What if numbers aren't just something we invented, but something we discovered? What if equations weren't tools to describe the universe, but clues to its true identity? Look closely. Every curve of a seashell, the spiral of a galaxy, the rhythm of a heartbeat, each follows invisible laws written in the language of mathematics. These aren't mere coincidences. They're signatures. Signatures of something deeper. For centuries, we've used mathematics to navigate, to build, to predict. But what if we've misunderstood its role all along? What if mathematics isn't just a way to understand the universe, but is the universe? From the tiniest particles to the largest cosmic structures, everything seems to obey patterns that arise not from matter, but from logic, pure, abstract, pristine. The universe, it seems, behaves not like a machine, but like a theorem. In this documentary, we'll journey beyond equations and formulas into a place where numbers breathe, where geometry molds reality, and where the fabric of existence may be nothing more than mathematics dreaming itself into form. This is not a story of science alone. It's a story of meaning, of truth, of the mysterious code that may underlie everything we know. This is the mathematical soul of the cosmos. Long before we built computers, launched rockets, or penned equations onto chalkboards, mathematics was already present, etched into the architecture of the natural world. It was there, in the spirals of galaxies, in the rhythm of heartbeats, in the quiet unfolding of leaves toward the sun. And yet, no one had written it. It existed independently of us, silently governing the mechanics of reality. We didn't invent it, we found it. The earliest mathematicians weren't scientists in lab coats. They were farmers, charting the seasons, builders aligning stones to the stars, and observers of the natural world who noticed that some things always seemed to happen in patterns. It began with counting, the most primitive form of math. 1 seed, 2 seeds, 3. 1 moon, full and then gone, then full again. From the repetition of days to the cycles of tides, early humans saw that nature was rhythmic, repeatable, almost mechanical in its fidelity. But as civilization advanced, the patterns we uncovered in nature grew far more elaborate, beyond mere cycles, into realms of astonishing precision. Perhaps the most famous mathematical pattern found in nature is the Fibonacci sequence, a series of numbers where each value is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, and so on. What seems like a simple number trick reveals itself in the most unexpected places. Look at a sunflower. Its seeds aren't scattered randomly. They're arranged in spiraling rows, curving outward from the center. Count the spirals in one direction, then the other. More often than not, you'll find Fibonacci numbers, 34 spirals one way, 55 the other. Pine cones, pineapples, and even the branching of trees follow this very same sequence. It's as though nature is following an invisible blueprint, one that dictates growth in terms of mathematical efficiency. This sequence is closely related to the golden ratio, approximately 1.618, a number that has captivated artists, architects, and scientists alike. The golden spiral, derived from this ratio, appears in hurricanes, galaxies, and nautilus shells. Why? Because it provides optimal packing, balanced growth, and aesthetic harmony. It's not just beautiful, it's practical. Evolution, it seems, has a taste for mathematics. But nature's relationship with math goes beyond numbers, into the realm of geometry. Snowflakes are iconic symbols of this idea. Each one is a frozen hexagonal miracle formed by the way water molecules bond at low temperatures. Despite the chaotic environment in which they form, their six-fold symmetry emerges with incredible precision. No two snowflakes are identical, yet they all obey the same geometrical logic. Bees, too, are master geometricians. Their hives are made of perfect hexagons, a shape that allows them to maximize storage while using the least amount of wax. Mathematically, the hexagon is the most efficient shape for tiling a flat surface without gaps. Somehow, through instinct and evolution, the bees have arrived at a solution that even Euclid would have admired. Spiders spin webs based on radial symmetry, lightning branches out in fractal patterns, and the human lungs mirror a recursive tree structure, each bronchus splitting into smaller and smaller parts, optimizing the exchange of gases in the most space-efficient way possible. These aren't just biological features. They are geometric solutions to physical problems. Mathematics isn't just embedded in space. It permeates time as well. Birds flap their wings in predictable frequencies. Cicadas in some regions emerge every 13 or 17 years, both prime numbers, perhaps as a survival tactic against predators whose life cycles don't match up. The beating of your heart, the blinking of your eyes, the firing of neurons, all of these follow patterns of frequency, amplitude, and timing that can be modeled and predicted mathematically. Even music, long considered the most emotional of human expressions, is ultimately mathematical at its core. A musical note is defined by its frequency. Harmonies arise when the ratio between two notes is simple and whole. A ratio of 2 to 1, or 3 to 2, or 5 to 4. Nature prefers whole numbers. Why do certain combinations of notes sound pleasing while others jar the ear? Because they either align or conflict with the mathematical waveforms that define them. And beyond sound, rhythm governs the biological clocks in all of us. Circadian rhythms, governed by the cycles of light and dark, influence our sleep, our hormones, and our energy. At every level, life is a symphony played in mathematical time. Zoom in beyond the biological, and math still reigns supreme. Crystals, for example, form in perfectly ordered atomic lattices. These structures, defined by symmetry and repetition, grow along axes of geometric regularity. Quartz, salt, diamond, all follow rules of tessellation that can be described with group theory and spatial matrices. These shapes aren't arbitrary. They're determined by the angles at which atoms bond, by the energy states they prefer, and by the laws of electrostatic attraction. Mathematics exists here, not as metaphor, but as law. Even at the molecular level, DNA, the very code of life, is a double helix, a structure with measurable twist angles, periodicity, and base pair spacing. The rules by which it coils, replicates, and expresses itself are dictated by statistical mechanics and probabilistic models. Once again, math is the quiet architect behind life itself. And what of the chaotic and unpredictable? Surely not everything in nature follows clean formulas and perfect ratios. Enter the realm of chaos theory, where even disorder follows rules. Weather systems, while seemingly random, are governed by non-linear dynamics, equations so sensitive that a tiny difference in initial conditions can lead to massive divergences over time. This is the essence of the butterfly effect. A small flap here, a hurricane there. Yet even chaos has structure. Lorentz attractors, strange loops, and fractals like the Mandelbrot set arise from equations that, while simple in form, create complexity beyond comprehension. Nature's messiness is not a flaw, but a deeper level of mathematics we're still learning to decode. Rivers carve fractal paths through landscapes. Mountain ranges display self-similarity where small portions resemble the whole. Clouds, coastlines, even blood vessels, these systems don't break the rules of math. They are math, rendered in recursive dynamic form. Here's the paradox that sits at the heart of it all. If nature follows mathematical laws so precisely, and if those laws existed before humans discovered them, then where did they come from? Consider this. No one told the sunflower to arrange its seeds by the Fibonacci sequence. No instructor taught the honeybee how to make a hexagon. The spider does not calculate the tensile strength of silk before weaving its web, and yet it forms a structure that engineers still try to replicate. These creatures follow instincts shaped by evolution, yes, but evolution itself operates according to mathematical models driven by probability, fitness landscapes, and statistical pressures. It's math all the way down. This raises a profound question. Is mathematics a human abstraction, or is it a fundamental property of the universe? Is the cosmos inherently mathematical, or does it just appear that way because our minds are wired to find patterns? Whatever the answer, one thing is clear: the universe, even in its most organic and untamed forms, behaves like a mathematical symphony, playing out across scales from the atomic to the cosmic. We often think of math as cold, rigid, lifeless, a set of rules imposed on paper, meant for classrooms and calculators. But in nature, mathematics is alive. It flows through rivers. It grows in leaves. It pulses in veins and echoes in the distant songs of galaxies. The natural world is not a static backdrop for mathematical exploration. It is the canvas, the brushstroke, and the equation itself. It's where math reveals its first great truth, that it is not confined to symbols, but manifested in reality. And if that's true, if the patterns of nature arise not from coincidence, but from some deeper logical necessity, then we must ask, what else might the universe be hiding in its mathematical core? In the next chapter, we'll leave the physical world behind and step into the realm of pure abstraction, where numbers exist without matter and geometry unfolds without space. A place that may answer a question too vast for physics alone. Do numbers exist even when there's no one there to count them? When you close your eyes and imagine the number 3, where does it exist? Not on the page, not in the air, and certainly not in the physical world, yet somehow it exists. The triangle, the square, the circle, these shapes aren't found in nature in their perfect form, but we all know exactly what they are. The laws of arithmetic don't rely on the universe to be true. 2 plus 2 will always equal 4, even if all matter were to vanish tomorrow. This gives rise to one of the most provocative ideas in all of philosophy and mathematics, that numbers, geometrical forms, and mathematical truths inhabit their own realm, one that is not part of the physical universe, but separate from it. A realm that is eternal, unchanging, and perfect. This is the domain of Platonic realism. Plato, the ancient Greek philosopher, believed that the world we perceive with our senses is only a shadow of a deeper reality. In his view, everything we see, the trees, mountains, people, and even stars, are imperfect manifestations of ideal forms. A circle drawn in sand is never perfect. But the idea of a perfect circle that exists in a realm beyond time and space. It is an eternal truth. It was not created and cannot be destroyed. It just is. Mathematics in this framework is not something we invent. It is something we uncover. We do not make triangles or define the number 7. We discover them. They were already there, waiting. This might seem like an abstract notion, but pause and consider, why does math work at all? Why do equations written by humans predict the behavior of planets, particles, and light with such uncanny precision? Why should a purely mental creation correspond so perfectly to the behavior of physical systems? Why is the language of the cosmos mathematical if math is merely a human construct? If mathematics had no independent existence, if it were merely a tool or invention, then why does it so reliably predict phenomena we haven't yet observed? Why does the equation exist before the measurement? Countless times in history, abstract mathematical structures, imagined in the mind and explored on paper, turned out later to describe real physical phenomena. Imaginary numbers, for instance, seemed absurd at first. Yet they are essential to understanding electrical circuits and quantum mechanics. Riemannian geometry was once a theoretical abstraction, and then Einstein used it to describe the curvature of spacetime. It's as if math knows something we don't, and we are just catching up. For Platonists, this is no mystery. Math is not an invention. It is the skeleton of reality. It exists in a separate ontological category, a shadowless place beyond time where every mathematical truth resides. We don't write math, we receive it, like signals from a deeper realm. This perspective is not universally accepted, but it is hauntingly powerful. If Platonic realism is true, then there exists a cosmic library of every mathematical structure possible, every shape, number, equation, and relation floating in a dimensionless space. And somehow, our universe taps into it. Perhaps reality is shaped not by matter, but by mathematics. Perhaps we are projections of patterns too pure to be seen. There is a kind of mysticism to this idea, yet it is also deeply rational. When a mathematician uncovers a new theorem, what has really happened? Has something new been born, or merely found? Even those who don't subscribe to Plato's ideas often describe moments of mathematical insight as discoveries, not inventions. As if these truths were waiting to be seen, already complete, like sculptures beneath marble, needing only the right mind to chip away the stone. If these forms are eternal, then they predate everything. Before stars, before atoms, before time itself, math was there. Not in symbols or numbers, but in relationships, in structures, in truths that did not need a universe to be real. And if so, then the cosmos itself might be a kind of imperfect expression of these hidden forms, a projection of invisible logic into visible matter. This raises profound questions. Are we part of the mathematical structure, or are we merely observing it from the outside? If we are made of the same logic we study, then to understand math is to look inward, to glimpse the architecture of our own existence. We are thinking matter, contemplating its own source. But what does it mean to live in a mathematical universe? Does this make us free, or are we bound by unbreakable equations? Are our lives guided by probability, symmetry, constraint? If math is the ultimate reality, then does free will even make sense? Or are we trajectories within a vast, multidimensional equation that plays out with cold elegance, unaware of the sentience it creates? And yet, even in this deterministic architecture, there is room for awe. The more we explore mathematics, the more we find beauty, simplicity, and interconnectedness. Equations that look different turn out to be the same. Patterns emerge across disciplines. A formula from topology finds use in genetics. A statistical method for gambling ends up explaining black holes. These are not coincidences. They are echoes of something deeper, something unified. If mathematical forms truly exist outside of space and time, then perhaps the universe is not just a machine made of particles, but a manifestation of thought. Not our thought, but thought itself. A kind of pure intelligence, a logic without a thinker, a language without a speaker. The cosmos becomes a poem, written in symbols no eye can see, but every atom obeys. In the end, Platonic realism is not just a philosophy of numbers. It is a radical idea about existence itself. It proposes that the material world is not the ultimate reality, that behind the veil of dust and stars is a deeper fabric made not of particles, but of form, and that to study mathematics is to press our fingers against the edge of the infinite, to listen, just for a moment, to the quiet song that built the universe. There exists a proposition so radical, so audacious in its implications, that it challenges not just our scientific understanding of the universe, but the very way we perceive existence itself. It is known as the mathematical universe hypothesis, and it was brought forth by physicist Max Tegmark with a disarming yet haunting simplicity that the universe is not merely described by mathematics, it is mathematics. In this view, the universe is not a canvas painted with the colors of equations. It is the canvas, the paint, the frame, and the hidden logic that allows painting itself. According to this hypothesis, every particle, every force, every moment of time, and every configuration of space is nothing more than a mathematical structure, an entity existing independently of human cognition, woven from numbers, patterns, symmetries, and axioms. We are not observers of the mathematical realm. We are embedded within it, conscious expressions of abstract relations. Tegmark's vision is not of a universe governed by mathematical laws, like a machine guided by instruction, but of a universe that is the law itself, the formula made flesh, the theorem in action. To accept this is to concede that reality's ultimate substrate is not physical but logical, that beneath the quantum foam and relativistic curvature lies not energy or mass, but pure, cold mathematics. In this vision, the electron is not a tiny sphere, but a manifestation of a specific mathematical symmetry. Space is not a void, but a topological framework defined by relational geometries. Even time becomes an emergent aspect of more fundamental mathematical constraints, not flowing like a river, but structured like a complex multidimensional lattice. The implications are staggering. If the universe is a mathematical structure, then every other mathematical structure must also exist in the same way. That is, there exists not just one universe, but a multiverse of all possible mathematical structures, each one as real as our own, each with its own rules, constants, and dimensions. We inhabit one such structure simply because it supports observers like us. In this level, 4 multiverse, as Tegmark calls it, all logically consistent mathematical systems have the same ontological status as our universe. What we call reality is merely one node in an infinite mathematical landscape. In such a scenario, every solution to every equation exists somewhere, and every coherent set of axioms corresponds to some universe. Our cosmos, with its seemingly fine-tuned constants and elegant laws, is no more unique than a specific triangle within the infinite realm of geometry. This hypothesis reframes everything. The mystery of why mathematics is so effective in physics evaporates, because mathematics is not a tool to describe the universe. It is the universe. We are not decoding an external cosmos with invented symbols. We are discovering aspects of the structure we are already a part of. Mathematics is not invented, but discovered, not imposed upon reality, but intrinsic to it. The illusion of randomness, chaos, and unpredictability in nature is a veil drawn over a deeper, more ordered substrate of formal logic and abstract consistency. But such a view is not without its philosophical tension. If all mathematical structures exist, what gives ours the illusion of temporal flow, of change, of entropy? In a realm where every structure is timeless, where all truths are eternally true, where does the experience of time arise? Tegmark suggests that conscious observers arise in mathematical structures complex enough to encode self-referential systems, entities that can model themselves and their surroundings, experiencing a succession of states that we interpret as time. Our perception of a present moment, our memories of the past, and our expectations for the future are not properties of the universe itself, but byproducts of our embeddedness within a particular type of structure. We are like subroutines in a vast computational theorem, traversing through layers of complexity we mistake for chronology. But then what of free will, creativity, and emotion? Are these two reducible to mathematical form? In Tegmark's cosmos, even these human experiences are emergent from mathematical relations, quantifiable, modelable, derivable. The longing in a poem, the turbulence of a storm, the orbit of a moon, and the decay of a muon, all are expressions of the same invisible syntax. Every passion, thought, and decision becomes an event in a vast solution space of equations. In this model, the sacred and the scientific collapse into the same cathedral of logic. For those seeking meaning in the stars, Tegmark's vision offers no comfort of divine intervention, yet it replaces that with a kind of mathematical divinity, an eternal, all-encompassing order from which all phenomena arise. The universe becomes not a place, but a proposition, not a thing, but a proof, not a miracle, but a manifestation. It is not just atoms in the void, but variables in a boundless theorem. Even the emergence of life, so often attributed to the chaotic play of chance, becomes inevitable in certain mathematical structures. Life is not an accident, but a property of specific geometries and dynamics. The same way that certain mathematical graphs inevitably produce stable patterns, certain universes inevitably give rise to consciousness. We do not exist because the universe allows it. The universe exists in such a way that entities like us must arise within it. This hypothesis, radical though it is, reframes the ancient question, why is there something rather than nothing? The answer, from this perspective, is that everything that can exist mathematically does exist, and we simply find ourselves in one such reality because it is among those that support perception. Tegmark's vision does not demand belief, nor does it rest on mystical assertion. It is a consequence of following the logic of mathematics to its ultimate end. It demands, however, a fundamental shift in how we see ourselves, not as observers standing apart from a cosmic machine, but as patterns within a self-aware equation, dreaming of stars while suspended in symmetry. In such a reality, the sacred number is not merely a circle's whisper. It is the heartbeat of a universe built not on stone or fire or void, but on the clarity of logic and the eternity of numbers. What if the universe is not merely governed by laws, but sculpted into existence by the quiet logic of symmetry, an abstract perfection echoed in every particle, every force, every unfolding moment in time? From the vast scale of galactic motion to the tiniest quark's spin, symmetry weaves an invisible architecture behind the phenomena we observe, a sacred order humming beneath chaos, dictating what can happen and forbidding what cannot, as though the universe is a self-enforcing poem written in the me language of invariance. This symmetry is not superficial or aesthetic, but structural and profound, whispering through the very fabric of reality like an ancient code. At the heart of this idea lies the extraordinary insight of Emmy Noether, whose theorem, a mathematical revelation cloaked in elegance, unlocked a secret doorway between symmetry and the physical laws themselves. She discovered that every conservation law, such as the conservation of energy, momentum, or electric charge, is not an arbitrary principle, but the consequence of an underlying symmetry in nature. The preservation of energy over time. That emerges because the laws of physics do not change from one moment to the next. The conservation of momentum? That exists because the laws of physics are the same here as they are over there. Like reflections in a mirror, like the petals of a flower, the balance in an equation maps directly onto the persistence of physical behavior. In this view, the very existence of coherent physics becomes inseparable from symmetry. Remove the symmetry, and the laws dissolve. It is not merely that the universe prefers symmetry, it is birthed from it. The cosmos, in all its vastness, may be nothing more than the crystallization of abstract symmetry into space-time. Dive deeper, and symmetry becomes a defining principle in the most advanced structures of modern physics. In the quantum realm, the Standard Model, the most successful theory of particle physics ever constructed, is nothing but an edifice of symmetry groups, abstract mathematical objects that dictate how particles interact, transform, and even exist. These groups, with cryptic names like SU3, SU2, and U1, are not arbitrary constructs, but the fingerprints of nature's underlying syntax. Every known fundamental force, electromagnetic, weak nuclear, and strong nuclear, arises from the requirement that the laws of physics remain invariant under specific transformations. Gauge symmetry, the central pillar of these interactions, ensures that the behavior of particles stays consistent even as we shift our perspective in abstract mathematical spaces. These aren't symmetries of space or time as we normally conceive them. They are symmetries of fields, rotations in invisible dimensions, exchanges of charge or phase that define the consistency of reality itself. When you change a field in a way that respects asymmetry, the physics remains unchanged, and this invariance is what gives rise to forces. Force, in this view, is not a push or a pull, but a manifestation of how nature compensates for preserving its internal symmetries. The photon, carrier of light, exists because of the invariance under a U1 gauge transformation. The gluons that hold atomic nuclei together spring from SU3 symmetry. Even the Higgs field, the mysterious presence that endows particles with mass, is a consequence of symmetry breaking, where a perfectly symmetrical system spontaneously selects a direction and thereby creates the illusion of asymmetry. The phenomenon of spontaneous symmetry breaking is itself a cosmic enigma, akin to a pencil balanced on its tip, suddenly falling in one direction, thereby creating an imbalance where none existed. In the early universe, when the energy was unimaginably high, the forces of nature were unified, indistinguishable, woven together in perfect harmony. But as the universe cooled, this symmetry fractured, and the singular force split into the four we now observe: gravity, electromagnetism, and the strong and weak nuclear forces. The emergence of structure, of complexity, of diversity is a byproduct of broken symmetry. But the brokenness is not chaos. It is a higher order disguised as diversity. The laws of nature emerge not in spite of symmetry's failure, but because of it. Even time itself, which seems to flow asymmetrically from past to future, may owe its arrow to a deeper symmetry that was broken in the universe's infancy. And yet, symmetry also defines the boundaries of what is possible. The reason why some particles decay while others remain stable, why matter can exist but antimatter is scarce, why we do not see certain interactions in particle accelerators. All of this is a direct result of symmetry rules encoded in the mathematical scaffolding of the universe. Violating these rules is not just unlikely, it is forbidden by the very geometry of reality's equations. The universe is not random in its behaviors. It dances within a permitted framework, choreographed by invariance. Every mathematical symmetry is a commandment carved into the logical bedrock of existence, and every particle is an obedient note in the cosmic symphony. This vision forces us to reframe the very meaning of physical law. Instead of laws being commands imposed upon reality, they are constraints that arise from the inherent self-consistency of abstract structures. It is not that matter was told to follow certain rules, but that only those patterns of matter which obey the underlying symmetries could ever emerge in the first place. In this sense, symmetry is not only a description of reality, it is a selection principle for existence itself. The multitude of universes that might exist in mathematical possibility are filtered by symmetry into those that are coherent, stable, and hospitable to structure. Ours is one such universe, not because it was chosen, but because its symmetries allow it to be. And yet, within this sacred order, there lies mystery still. Why these symmetries and not others? Why U3 and not a larger group? Why do certain symmetry violations, like CP violation in particle physics, exist subtle but significant, introducing asymmetries into a mostly balanced world? Such questions are at the frontier of modern physics, where theorists search for a grand unification, a deeper symmetry from which all others descend. Some imagine that beyond the standard model lies a larger symmetry waiting to be discovered, like a forgotten root from which all visible branches grow. Others turn to string theory, where 10-dimensional symmetries vibrate in hidden dimensions, dictating not just particles, but the essence of space and time itself. Still others dream of even higher symmetry spaces, exceptional Lie groups, and infinite dimensional algebras that might one day reconcile gravity with the quantum. In each of these quests, symmetry is the compass, the guiding whisper from the void that says, "Follow the invariant, and truth shall emerge." The ancients saw beauty in symmetry, in the proportions of temples and the orbits of planets, sensing a divine harmony at work. Modern physics has stripped away the mythology, but kept the awe. For in symmetry, we do not just find elegance, we find necessity. The cosmos does not merely prefer symmetry, it demands it. And in that demand, it reveals its soul, not through chaotic impulse, but through the relentless mathematical quietude of what must be. The laws of nature are not separate from the equations. They are born from them, shaped by the constraint that symmetry imposes, and illuminated by the insight that to know the invariant is to know the intermitted. In that stillness, the universe breathes, perfectly balanced on the edge of logic and possibility, a crystalline lattice of patterns, too deep to see yet too powerful to escape. Beneath the elegant scaffolding of the Standard Model, beneath even the mysterious veil of quantum fields, lies a domain more abstract than energy or matter, a realm where particles are not entities in the traditional sense, but manifestations of pure mathematics. Here, in the crystalline palace of group theory, the hidden structure of reality is not built of atoms or strings, but of symmetries and transformations, encoded in the silent logic of algebra. Group theory, the branch of mathematics concerned with symmetry, has become the master key to unlocking the identity of particles, the classification of forces, and the choreography of their interactions. At its core, a group is simply a set of operations that can be performed and undone without ever stepping outside the set, a framework of transformation rules that defines internal consistency. Yet when this deceptively simple concept is extended to continuous transformations, to rotations and phase shifts and internal changes that leave the underlying physics unchanged, it blossoms into something astonishing, the architecture of everything. In particular, Lie groups, named after the Norwegian mathematician Sophus Lie, capture continuous symmetries in smooth, infinitely small transformations, the kinds that define the laws of motion and the seamless interactions of fields. These groups do not describe particles in the way a chemist describes an atom. They dictate what a particle is, reducing identity to a position within an abstract algebraic space. The mass, charge, spin, and even interaction strength of a particle are not intrinsic characteristics like color or shape. They are the consequences of how that particle transforms under the operations of certain symmetry groups. Bores? In this sense, particles are not fundamental. They are shadows cast by the deeper symmetries of the mathematical void. To understand this idea is to confront one of the most radical propositions in science, that all the complexity of matter emerges from patterns of transformation. The Standard Model itself is not just a theory of particles. It is a grand structure built from three symmetry groups combined, SU3, SU2, and U1. Each of these Lie groups represents a kind of internal symmetry, a way of transforming fields that leaves the physical content of the theory untouched, and yet, paradoxically, gives rise to observable phenomena. The U1 symmetry underlies electromagnetism, dictating the behavior of photons and electric charge. SU2 governs the weak nuclear force, responsible for radioactive decay and the workings of the sun. SU3 orchestrates the strong nuclear force, binding quarks into protons and neutrons via the exchange of gluons. These groups are not philosophical concepts. They are mathematical structures with concrete rules, and every known particle fits into them like a note in a cosmic musical scale. Quarks, for example, are defined not by what they are made of, but by how they transform under SU3. They come in 3 colors, not because of anything visual, but because SU3 has 3 fundamental ways of labeling transformations. Gluons, the carriers of the strong force, are nothing more than the generators of SU3, the mathematical operators that enact the group's symmetry. Similarly, leptons like the electron and neutrino belong to representations of SU2 and U1, and their interactions are governed entirely by how these symmetry groups combine and intertwine. There is no hidden layer beneath this. The behavior of these particles flows directly from the algebraic properties of the groups they inhabit. Even the quantum numbers we use to describe particles, like electric charge, isospin, and hypercharge, are not arbitrary or empirical, but arise from the structure of these symmetry groups. In fact, the reason why the electron has the exact charge it does, why the double U and Z bosons are massive while the photon is massless, and why the Higgs boson exists at all, can all be traced back to how these groups break or remain intact. Symmetry breaking in this algebraic context is not a flaw. It is the genesis of difference. Before symmetry breaks, the particles are indistinct, like colors smeared on a palette. When the symmetry fractures, distinctions emerge and mass arises. The Higgs field, central to this process, is a scalar field whose vacuum expectation value breaks the SU2 multiply by U1 symmetry down to U1, giving mass to the double U and Z bosons while preserving the masslessness of the photon. This process is not a mechanical accident, but a precise operation encoded in group theory, where the vacuum itself chooses a direction in abstract space, collapsing the symmetry and revealing the particles we observe. Thus, even the so-called empty vacuum is a decision point in an algebraic hierarchy, a background chosen from an infinite symmetry space. Delving deeper, we find that group theory also explains why certain interactions are allowed and others are forbidden. Conservation laws, such as conservation of electric charge or lepton number, are not inserted into the theory, but emerge naturally from the invariance of the Lagrangian under these group transformations. In quantum field theory, the Lagrangian, the mathematical object that describes the dynamics of the system, must remain unchanged under symmetry operations. This demand of invariance leads inevitably to the interactions we observe and prohibits others. The result is that the universe is not an anything-goes arena. It is a tightly governed structure where even the rarest processes must obey the dictates of abstract algebra. Particle decays, reaction probabilities, and scattering behaviors are all pre-written in the language of group representations. Even when particles change identity, when a muon decays into an electron, for example, they do so by following paths permitted by symmetry rules. In this sense, the universe behaves like a massive, multi-dimensional Rubik's Cube, where every move, twist, and transformation is sanctioned by group theory. These higher symmetry groups predict new particles, relationships, and interactions that have not yet been seen, but if detected, would provide evidence that our universe is even more deeply unified than we imagine. In string theory, the most ambitious attempt at unification, particles are not points but vibrating strings, and their vibrational modes correspond to representations of enormous symmetry groups like E8 times E8. Here, the geometry of extra dimensions and the algebra of symmetry merge, suggesting that even space-time itself is not fundamental, but an emergent property from group-theoretic dynamics. In such frameworks, the universe is a manifestation of the way symmetry can fold, twist, and ripple in mathematical space, generating particles as musical harmonics in a cosmic algebraic symphony. Thus, when we ask, what is an electron? Or, what is a quark? We are not asking about physical substance in the classical sense, but about an algebraic identity, an element in a symmetry space, a mode of transformation under a particular group. Matter is no longer the starting point. It is the endpoint of mathematical necessity. The universe is not built from things, but from relationships, from the abstract ways in which fields can twist and turn without violating the invisible constraints of group theory. In this vision, reality is not material, it is structural. To understand the universe is not to know what it is made of, but to know how it transforms, how it maintains its balance as it evolves, and how every dance of particles is choreographed by the algebraic symmetries written into the fabric of existence itself. The cosmos is not a machine, but a proof, an unfolding argument from premise to consequence, governed not by objects, but by transformations, and revealed not in shapes, but in the harmony of symmetries that define what can be. The particles we see are not the building blocks. They are the notes in a higher mathematics, and group theory is the score by which the universe plays its eternal song. The quantum realm. Strange, counterintuitive, and yet astonishingly accurate, does not resemble any terrain we can touch or see. Here, objects have no definite positions or momenta until measured. Particles exist in multiple states at once, and causality itself seems to hang on a probabilistic thread. Yet, through all this conceptual chaos, quantum mechanics functions with an eerie precision, not because it describes the quantum world, but because it is the quantum world. The language of the quantum isn't just mathematics. It is mathematics in its purest, most abstract sense. At its foundation lies the concept of the Hilbert space, a complex, infinite-dimensional vector space that houses the wave functions of particles. Every quantum state is not a point in space, but a vector in this mathematical cosmos, defined not by coordinates, but by probability amplitudes. These amplitudes are not ordinary probabilities. They are complex numbers, quantities with both magnitude and phase, that interfere and superpose, leading to the rich tapestry of quantum phenomena. The square of the magnitude of these amplitudes gives the probability of observing a particular outcome, but their true magic lies in their capacity to interfere. Destructive and constructive interference between amplitudes allows particles to simultaneously explore all possible paths, only collapsing into definite outcomes upon observation. This strange behavior has no classical analog, but it is entirely natural within the geometric and algebraic structure of Hilbert space. Operators in this realm act as the mechanisms of change and observation. In classical mechanics, a system state evolves according to differential equations, but in quantum mechanics, evolution is governed by the Schrödinger equation, a differential equation not of particles but of wave functions. The Hamiltonian operator, a mathematically defined construct, dictates how quantum states evolve over time. Measurement, too, is not an act of peeking into a box, but a projection operation where an operator selects a basis and the system's state vector collapses onto one of its eigenstates. The observable quantity whether position, momentum, spin, or energy, is linked to a Hermitian operator, ensuring real eigenvalues and a measurable spectrum. This projection is not an artificial overlay. It is the only known way to connect the mathematical wave function with the concrete experience of outcome. Before measurement, the system is not in one state or another. It is a superposition of all possible states, encoded with delicate phase relations. After measurement, the wave function collapses into a single eigenstate, the outcome of which is determined by the modulus squared of its amplitude. This mathematical act, projection in a vector space, is the mysterious boundary between the potential and the actual, the abstract and the physical. The entire process has no need for physical modeling. The math itself is the medium of reality. Entanglement, perhaps the most mystifying quantum feature, arises naturally in this mathematical playground. When two or more systems are described by a joint wave function in a tensor product of Hilbert spaces, their properties can become non-factorizable. They cannot be described independently. Such systems are said to be entangled, and their correlations persist regardless of spatial separation. This is not a spooky action at a distance, but a mathematical property of the joint wave function. The individual particles cease to have their own states. Only the global state of the system remains well defined. Measurement on one part of the system instantaneously affects the probabilities for measurement outcomes on the other, not because of a signal, but because the mathematical structure does not permit the separation of their states. This non-locality has been experimentally verified, yet it does not violate the principles of relativity precisely because it operates within the domain of information, not causality. Here again, the mathematical architecture defines the rules. There is no hidden layer behind the equations, no unseen gearwork generating the correlations. The algebra itself is the physics. Quantum fields further reinforce this perspective. Quantum field theory, the framework that marries quantum mechanics with special relativity, treats particles not as objects, but as excitations of underlying fields. These fields are themselves operator-valued functions defined over spacetime, and their dynamics emerge from path integrals, commutation relations, and Lagrangian densities. Every particle arises from the quantization of a field, and the interactions among them emerge from terms in the Lagrangian that respect specific symmetries and conservation laws. But this entire edifice, fields, particles, forces, is built entirely from mathematical constructs. The fields live in abstract spaces, and their evolution is described not by physical motion, but by transformations in function space, constrained by algebraic rules. Path integrals, an alternative formulation of quantum mechanics, sum over all possible histories between initial and final states, weighted by a complex exponential of the action. These sums are not metaphorical. They are genuine mathematical operations, and their output matches physical experiments to incredible precision. Thus, the universe at its most fundamental level doesn't act like a machine. It computes like an algorithm, obeying rules set by operator, algebras, complex manifolds, and probabilistic flows. Nowhere is this more evident than in the phenomenon of quantum tunneling. In classical physics, a particle cannot cross a potential barrier higher than its energy. But in quantum mechanics, the wave function does not obey such restrictions. Since it evolves continuously through configuration space, it can have non-zero amplitude beyond the barrier, leading to a finite probability of detection on the other side. There is no physical mechanism forcing the particle through. Rather, the mathematical structure of the wave function simply permits it. It's as though the laws of being are defined not by resistance or substance, but by what is allowed in the solution space of a differential equation. The fact that the universe obeys such logic-based outcomes suggests that physicality is emergent, not primary. Even phenomena like the Casimir effect, quantum fluctuations, and virtual particles, once considered arcane, now find neat explanations in terms of vacuum expectation values, Fourier expansions, and algebraic regularization schemes. These are not tricks to approximate reality. They are reality. This perspective has radical implications for our understanding of existence. If the quantum world is built entirely from mathematical objects, then reality itself is an instantiation of a mathematical structure. There is no deeper layer underneath the wave function, no set of billiard balls hiding behind the abstractions. What we call a particle is just a peak in probability amplitude, a ripple in complex number space governed by linear operators and symmetries. The rules that govern these interactions are not discovered through trial and error. They are demanded by internal consistency. Quantum mechanics does not just describe the behavior of particles, it defines what it means to behave. In this sense, mathematics is not a tool used by the universe. It is the universe's essence. The only reason quantum mechanics works so perfectly is because it has no alternative. Once you accept the principles of superposition, unitary evolution, and measurement via projection, the rest follows logically and unavoidably. This is not merely a framework. It is the grammar of the cosmos. So, we are left with a staggering realization that everything at the quantum level, energy, matter, causality, identity, is born from and governed by abstract mathematics. Our deepest experiments confirm this, not by showing us physical gears behind the veil, but by validating equations and eigenstates, amplitudes, and matrices. The quantum world doesn't hide reality. It is reality, written not in clay or light, but in vectors, operators, and complex spaces. We are not observers of a material machine, but participants in a vast, evolving mathematical tapestry where reality is calculated, not constructed. Imagine a universe where geometry is not a byproduct of physical form, but the origin of it, where space is not the container for matter, but matter is the expression of space's shape. In this vision, geometry is not merely a way to describe the world, but the world itself, encoded in its most primal syntax. The evolution of this idea begins in a flat world, a realm famously explored by Edwin Abbott in his allegorical novella Flatland, where two-dimensional beings navigate a reality they cannot fully comprehend. Their blindness to the third dimension mirrors our own limitations in perceiving higher geometries. Yet in modern physics, we now accept that dimensions beyond our perception may not just be mathematically valid, they may be fundamentally real. General relativity was the first major step in elevating geometry to the status of physical law. It showed that gravity is not a force in the traditional sense, but the curvature of space-time itself. Matter tells space how to curve, and curved space tells matter how to move. This elegant marriage of geometry and physics replaced Newton's invisible forces with the pliable, four-dimensional fabric of reality. Every trajectory, every orbit, every wave of light bends not because of an external cause, but because it is tracing a path through warped geometry. Black holes are not objects, but regions where geometry becomes so extreme that even light cannot escape its grasp. This interpretation of the cosmos, where the fundamental interactions emerge from space-time's geometric structure, suggests that to study shape is to study substance. The progression from general relativity to even deeper geometrical theories did not stop there. As physicists tried to reconcile quantum mechanics with gravity, they encountered a serious challenge. Space-time itself seemed to break down at the Planck scale. The smooth continuum assumed by relativity could no longer handle the wild fluctuations of quantum energy. This led to the hypothesis that perhaps geometry, too, is quantized. Loop quantum gravity, for instance, suggests that space is composed of tiny, discrete loops, forming a spin network, an abstract, combinatorial geometry where areas and volumes are quantized. These networks evolve over time via spin foams, giving rise to an emergent spacetime that is fundamentally granular. In this model, the flowing fabric of the universe is made of indivisible geometrical units, nodes and links that stitch together the cosmos, not unlike pixels on a digital screen, but governed by algebraic rules and topological constraints. There is no smooth space underneath. Geometry itself is quantized into a mathematically governed lattice of connectivity. Even more ambitious is the geometrical vision proposed by string theory. Here, the basic building blocks of the universe are not zero-dimensional particles, but one-dimensional vibrating strings. Each vibrational mode of a string corresponds to a different particle, with its properties, mass, charge, spin emerging from the geometry of the string's vibration. But for the mathematics to be internally consistent, strings must exist not in the familiar 4 dimensions, but in 10 or even 11. These extra dimensions are not arbitrary. They are required by the mathematical structure of the theory, and their shapes are described by intricate geometrical forms known as calibi, Yo manifolds. These compact multi-dimensional shapes are not just abstract curiosities. They determine the physical properties of our universe. The way they fold, twist, and interconnect defines the spectrum of particles, the forces between them, and the constants that govern physical interactions. Our visible universe may be a 3-dimensional shadow cast by a much richer, higher-dimensional geometry curled up at subatomic scales. The implication is staggering. The fabric of everything we observe, particles, fields, forces, is woven from the topology of unseen dimensions. Further still, the holographic principle introduces a radical geometrical reinterpretation of reality. According to this idea, all of the information contained within a volume of space can be described by information encoded on its boundary. This concept, born from black hole thermodynamics and later formalized in the anti-de Sitter correspondence, suggests that our 3-dimensional universe may be the projection of a more fundamental 2-dimensional geometrical structure. In this holographic model, volume itself becomes an emergent property derived from correlations along a surface. Geometry here is not just the scaffolding of space, but the syntax of information, the way data is organized and distributed across dimensional boundaries. This has led to explorations of entanglement geometry, where quantum entanglement patterns give rise to the very shape and structure of spacetime. The boundary between physics and geometry vanishes, replaced by a landscape where entangled information determines distance, shape, and dimensionality. Mathematics also explores non-Euclidean geometries, spaces that defy common intuition. Hyperbolic spaces, spherical manifolds, and other exotic topologies have been harnessed to model the universe at cosmic scales. Cosmological measurements suggest that space-time may be flat, but models allow for slight curvature, allowing the geometry of the entire cosmos to be either open, closed, or infinite. These large-scale geometries influence the fate of the universe itself, whether it will expand forever, recollapse, or coast into stasis. Here, geometry doesn't just explain physical law, it dictates cosmic destiny. Similarly, in the study of topological quantum field theories, the geometry of space becomes a player in determining the properties of physical fields, leading to exotic phenomena such as topological insulators, anyons, and quantum Hall effects. These are real-world manifestations of abstract geometry, where the twist and braid of mathematical space manifests in stable, measurable states of matter. Furthermore, geometric dualities provide a lens into the unity behind seemingly disparate theories. Mirror symmetry, for instance, reveals that two different calibi, Yau manifolds, can lead to equivalent physical theories, implying a hidden symmetry not between particles, but between geometries themselves. T-duality and S-duality in string theory show that small and large dimensions can be interchanged, or that strong and weak coupling regimes are geometrically connected. These dualities are not superficial. They suggest that the true nature of reality lies not in any particular geometrical representation, but in the abstract equivalences between them. Geometry becomes not just reality, but the meta-reality, the underlying logic that transcends individual formulations. Even time, often treated as a distinct entity, is being re-evaluated through geometric lenses. In various quantum gravity approaches, time emerges not as a fundamental parameter, but as a byproduct of change within a geometric network. In causal set theory, space-time is a growing graph of discrete events ordered by causality, with geometry arising from the network structure. The passage of time is no longer a flow, but an unfolding of new connections. Similarly, in twistor theory, geometry is recast in terms of complex space, where the fundamental objects are light rays and null surfaces, and space-time points become derived entities. This inversion of the usual hierarchy further cements the idea that geometry is not a description of space. It is the primal reality from which space, time, and matter derive. Thus, from the rigid abstractions of Euclidean planes to the vibrating folds of string manifolds and the foamy networks of quantum geometry, the progression of physics consistently points to a singular revelation. Geometry is not a map of the territory, it is the territory. The shape of things is not secondary to their being, it is their being. Matter is geometry that vibrates. Force is geometry that curves. Time is geometry that changes. In the mathematical soul of the cosmos, form is function, and function is law. To uncover the secrets of existence, one does not dig into particles or energy fields, but into the architectures they arise from, into the multidimensional symmetries, the compactified curves, the entangled surfaces, and the topological links that define not just how the universe looks, but what is. If reality is mathematical, then the architecture of that reality is constructed not merely of numbers or geometry, but of logical systems, formal structures that define what can be known, what can be proved, and ultimately what can exist. It is in this conceptual territory that the ideas of Kurt Gödel emerge like fault lines under an otherwise seamless mathematical landscape. Gödel's incompleteness theorems, formulated in the early 20th century, detonated the assumption that mathematics, if built on a solid set of axioms, could be both complete and consistent. His first theorem declared that in any formal mathematical system rich enough to include arithmetic, there will always be true statements that cannot be proven within the system itself. His second theorem went further. Such a system cannot even prove its own consistency. This revelation shattered the dreams of foundationalists like David Hilbert, who believed mathematics could one day be formalized into a perfect, self-contained edifice of absolute truth. Instead, Gödel revealed that the mathematical universe contains shadows, statements that are true, but forever unreachable by proof. In a cosmos said to be governed by mathematical law, this poses a deeply unsettling question. Could the universe itself harbor truths that, while real, lie beyond any logical derivation? Could physical phenomena exist that resist reduction to fundamental axioms, not because they are complex, but because they are inherently unprovable within the system of nature's logic? If we take seriously the notion that the universe is mathematics, not merely described by it, but constituted of it, then Gödel's theorems are not abstract curiosities, but existential boundaries. They imply that any theory of everything, any final unifying equation of the cosmos, must necessarily leave something out, some corner of physical law, some whisper of behavior or structure that remains beyond the reach of derivation. Even if we possessed a perfect set of physical laws, there would be consequences of those laws we could never demonstrate from within the system. This shakes the dream of complete scientific determinism at its root. It suggests the possibility that the cosmos might be constrained by a logical architecture that is itself unable to account for all that it generates. Like a language that can describe its syntax, but not all the truths within its poetry, the mathematical cosmos might be full of realities that defy internal explanation. In this light, incompleteness is not a failure of understanding. It is a structural feature of any formalized cosmos. There will always be gaps between what exists and what can be shown to exist, between what is real and what can be revealed. Gödel's work is often considered alongside the Turing halting problem, which proved that there is no algorithm capable of determining, for all cases, whether a given program will eventually halt or run forever. This, too, is a limit not of computing power, but of computability itself. If the universe operates like a vast computational process, then Turing's results imply that there will be phenomena whose outcomes we cannot predict, not because of ignorance or complexity, but because of inherent undecidability. The intersection of Gödel and Turing places profound restrictions on the dream of an omniscient cosmic equation. It paints a picture of a universe where some aspects are inherently opaque, fundamentally hidden not by distance or energy scales, but by logic itself. These theorems do not merely constrain human understanding, they define a boundary between knowable and unknowable reality. They delineate a kind of metaphysical event horizon, not in space, but in thought. Moreover, Gödel's impact reaches into physics in subtle but profound ways. In 1949, he shocked Einstein and the scientific community by constructing a solution to the equations of general relativity that allowed for closed time-like curves, essentially loops in time. The so-called Gödel universe permitted time travel without violating the equations of motion. This wasn't merely a curiosity, it was a demonstration that mathematical consistency does not always align with physical plausibility. The logic of the equations allowed solutions that challenge causality and intuition. This suggests that even in the precise arena of physical law, logic itself might stretch beyond the bounds of experience. The physical world, it seems, may be embedded within a mathematical system whose own internal consistency produces realities we struggle to interpret or even accept. If logic can permit such exotic realities, then perhaps the limit of the real is not set by nature, but by interpretation. At the heart of GDL's work is self-reference, the idea that a system can encode statements about itself. In mathematics, this creates paradoxes, such as the famous liar paradox or Russell's paradox in set theory. But self-reference may also have implications for consciousness, complexity, and even cosmology. If the universe can encode knowledge of itself through observers, through evolution, through recursive systems, then it too is a self-referential structure. But GDL teaches us that self-reference inevitably leads to limits on what can be resolved within the system. Applied to the cosmos, this could mean that the universe, in attempting to understand itself through science, may encounter boundaries not of scale or instrument, but of logic. There may be questions that no amount of empirical investigation can resolve, because the system, the cosmos, cannot contain proofs of all its own truths. In this view, mystery is not temporary, it is fundamental. This idea also challenges the nature of physical law. If laws are mathematical statements, and mathematics is constrained by incompleteness, then perhaps the laws themselves are not final. There may be truths of nature that are not derivable from any foundational set of equations, but instead exist as orphaned facts, real but formally unprovable. This opens the possibility that some constants of nature, say the fine structure constant or the mass of the electron, might not be derivable from deeper principles, but are simply true in a GDLian sense, part of the structure, yet inexplicable from within it. If so, the pursuit of ultimate explanations might reach a point of principled futility. The universe would still function with perfect regularity, but the reason for that regularity would elude all internal systems of logic. There is also the question of multiverses. In various cosmological models, our universe is one of many, each governed by slightly different parameters or laws. If this is true, then perhaps each universe is a different formal system, each with its own set of GDLian blind spots. Our own cosmos may be unable to perceive or compute aspects of other universes, not because they are distant, but because their axioms render them logically invisible to us. Conversely, some universal truths might reside only in the metasystem, the multiverse itself, just as some mathematical truths lie outside any single formal system. In this context, GDL's theorems suggest that no universe, not even the multiverse as a whole, can be both completely self-contained and logically closed. There will always be truths floating beyond formal grasp, like islands in a mist of abstraction. Even the notion of physical reality becomes slippery in light of incompleteness. If our universe is the output of some deeper informational process, a cosmic code, a simulation, a divine computation, then GDL implies that there will always be aspects of that code that are true yet undecidable. In a simulated cosmos, this would mean there are behaviors or phenomena that arise not from the rules of the simulation, but from the meta-rules that govern the simulation's logic. These could never be deduced by entities inside the simulation. If our cosmos is such a system, then it may contain shadows of truths forever out of reach, not because they are not real, but because we are bound by the limitations of our logical frame. Thus, in the quiet rigor of mathematical logic, G. Deal revealed a paradox at the heart of all knowledge systems, that truth is wider than proof, that reality is broader than understanding. If the cosmos is indeed mathematical, it cannot be both fully self-explaining and logically consistent. It must contain mysteries, not of darkness or ignorance, but of structural necessity. G. Dell did not impose this barrier on mathematics, he uncovered it. And in doing so, he may have revealed something even deeper about the universe itself, that the limits of logic are not the end of inquiry, but its beginning. When we reach the terminus of inquiry, past the particle fields, the shifting geometries of spacetime, the hidden logic of algebraic symmetries, and the layered abstract structures that hold quantum phenomena in delicate balance, we are confronted with a startling realization that the universe may not merely follow mathematical rules, but be mathematics in its very essence. Not a metaphor, not a description, but an identity. The world we see, the expansion of galaxies, the rotation of moons, the entanglement of photons, the curvature of spacetime, is perhaps not just mirrored by mathematical language, but arises from it as shadows arise from the shape of the object casting them. This idea, while seemingly poetic, carries immense ontological weight. It suggests that behind every observable fact is an invisible architecture of relations, a scaffolding that is not material, but formal, not constructed of substance, but of logic, patterns, and structure. Such a perspective reorients our entire conception of existence. Matter is no longer primary. Particles are not indivisible units of reality, but expressions of symmetries in abstract mathematical spaces. Forces are not things, but derivatives of the way these abstract spaces curve, twist, and connect. Time itself is not ticking from some primordial clock, but emerges from deeper relational flows within this invisible lattice of mathematical being. To reflect on a universe that is mathematics is to blur the line between reality and abstraction. If everything physical is reducible to interactions, and interactions to rules, and rules to relations, then the physical world dissolves into a vast self-unfolding tapestry of logic. In such a reality, space becomes a set of coordinates, not in emptiness, but in meaning, each point defined by its relations to all others, like notes in a chord rather than pebbles in a sandbox. The vacuum, far from being nothing, becomes the canvas on which quantum fields oscillate, like vibrating equations, forming the particles we interpret as something. The elegance of physics, the way conservation laws arise from symmetries, the way particles are representations of groups, the way geometry gives rise to dynamics, ceases to be surprising. It is not that the universe just happens to be intelligible through mathematics. It is intelligible because it is mathematics. The mathematics is not a tool external to nature. It is the latticework from which nature is born. This concept challenges the long-standing philosophical division between the material and the abstract. Plato glimpsed it with his realm of ideal forms, timeless, perfect entities of which the physical world was but a dim reflection. In our era, this philosophical intuition has been recast in the language of theoretical physics. The laws that govern black holes, cosmological inflation, quantum coherence, and symmetry breaking do not appear to evolve arbitrarily over time or vary across space. They are constants, foundational statements that appear as if plucked from some deeper Platonic realm. And as our understanding deepens, we find these laws becoming less mechanical and more relational, less descriptive, and more generative. The electron is not merely a thing with mass and charge. It is the lowest energy excitation of a quantum field, an object defined purely in terms of mathematical rules and constraints. Its identity is not intrinsic, but contextual, like a musical note defined by its place in a scale. The more we peel back the empirical layers, the more we find ourselves not in a laboratory, but in a cathedral of logic, one where proof and theorem illuminate the cosmos more deeply than light ever could. But to declare the universe mathematical is not to deny wonder, mystery, or meaning. On the contrary, it enhances them. If reality is rooted in mathematics, then existence itself becomes an expression, a theorem being unfolded, an equation being solved, an infinite fractal spiraling through forms we can only partially perceive. In such a universe, consciousness too becomes not an anomaly, but a recursive structure within the larger informational flow, a feedback loop where the universe contemplates its own logic. We are the mathematics thinking about itself, embedded expressions reflecting on the totality. And perhaps this reflection is not just incidental. Perhaps the very emergence of awareness is the cosmos reaching a point of internal self-reference, where abstraction becomes aware of abstraction, and the equation includes the active interpretation within itself. This opens the door to existential questions. If the universe is mathematics, then what is the role of creativity? Are we discovering eternal truths or inventing structures within a vast logical possibility space? When we build new mathematical systems, non-Euclidean geometries, higher dimensional topologies, novel algebraic frameworks, are we expanding the fabric of what can be real, or merely exploring paths that were always there, waiting to be walked? If each consistent mathematical structure has its own internal logic, then perhaps each could give rise to its own kind of reality, a parallel cosmos with its own laws, its own space and time, its own forms of intelligence. Our universe, then, would be just one island in an infinite archipelago of mathematical possibility, selected perhaps by its capacity to support complexity, stability, or observers. In this light, existence becomes not an accident, but a kind of mathematical inevitability. Where the rules permit richness, reality flowers. And yet, for all the power of this vision, there remains a question that haunts even the most rigorous formulations. Why these equations? Why this particular Lagrangian for the standard model? This cosmological constant, this dimensionality? If mathematics is infinite, why does the universe select from such a narrow band of its possibilities? This question is not answerable from within the system, as GDL's shadow reminds us. There may be no ultimate proof as to why this particular slice of mathematics realized itself in existence. Or perhaps the question itself is malformed, asking why where there is only what. But even this epistemic boundary does not diminish the astonishing realization that we live in a cosmos where reason works, where logic binds, where numbers resonate with being. A cosmos where beauty in an equation predicts phenomena in the sky, where patterns etched in chalk become particles discovered in accelerators, where counting gives rise to quarks and symmetry births gravity. It also forces a reevaluation of our place within this grand structure. If the cosmos is mathematical, then we are not separate observers peering in. We are part of the structure itself. Our minds are not glitches in the system, but local configurations of logic capable of reflecting on the whole. We are not just in the universe. We are the universe, temporarily shaped into thought, inquiry, curiosity. And as we ask these questions about the nature of space, of time, of being, we do not step outside the system, but deepen our immersion in it. Each act of discovery is the cosmos folding back on itself in understanding. Each theorem proved, each principle grasped, is a moment in which structure becomes aware of structure. So what remains at the end of this intellectual odyssey, this journey through the mathematical soul of the cosmos? Not certainty, but a profound sense of coherence. The universe may be strange, even incomprehensible in parts, but it is not arbitrary. Its operations are intelligible because they are structured. Its mysteries are not gaps in knowledge, but invitations to explore deeper realms of relation. And in this exploration, we participate in the very unfolding of the cosmos, not as outsiders, but as agents within the system, a system built not from atoms and void, but from relations, logic, structure, and form. The universe is not a thing. It is a statement, a vast, ongoing proposition. And in seeking to understand it, we are not just solving a puzzle. We are answering the most beautiful equation of all, the one that includes ourselves within its terms. And so, as we close this journey through the invisible lattice of logic that binds reality, we are left with a stunning proposition that existence itself is not built from atoms or energy, but from relationships, from symmetry, from number. The stars above us, the time that flows through us, and the thoughts that arise within us may all be echoes of an eternal structure, one not written in stone, but etched in the language of mathematics. This is not the cold precision of a lifeless grid, but the living pulse of a universe that dreams in equations. We are not separate from this grand design. We are not passengers observing from the sidelines. We are the very geometry folding into self-awareness. The mind that contemplates the cosmos is itself a product of its patterns, a recursive ripple in an infinite sea of logic. Perhaps this is the deepest truth of all, that to understand the universe is to glimpse the mind of mathematics itself, and to see in that reflection our own. Reality is not made of things. It is made of truths. And we are the question the universe asks itself, and the answer that keeps unfolding.